Hello once again, and we're continuing with our series in statistics. Today's topic is the Central Limit Theorem for proportions, so let's begin. This is presentation 7.6, and the topic is the Central Limit Theorem for proportions. We want to acknowledge the development team of Brad, Spencer, Amanda, and myself. And as an illustrative problem which we've discussed in previous presentations, we have here a bird flu outbreak, and health officials suggest that an infection rate of 20%, and they begin to investigate this possibility here. And we're suggesting that this model represents a binomial random variable, and trials and so on. Feel free to pause the video and take notes. We take a sample of size 64 and compute x equals the number of successes in 64 trials. This gives us 14 out of 64, 21.9%. And repeating that again for 64 trials, found 12, that's 18.8%. And we have coming on the screen here these sample proportions, and you'll note that typically they will cluster around 20%. They'll be normally distributed, as seen coming on the screen here. They build up around the 20% if that's true, and the mean of the p-hats will be around 20%. And the standard deviation given by this expression here is plus or minus 5%. And this suggests that that represents a 68% interval about the population proportion, within which, of course, 68, 2 to every 3 will fall. And we're going to apply that to come up with a 95% confidence interval. Now, a 95% confidence interval associated with a z-score, z-score, plus or minus 1.96, times your standard error, giving rise to the margin of error of plus or minus 0.098. This is called your 95% margin of error. And now we're going to look at 95% of the p-hats will fall between these two red lines. One on average will not. And if we simply measure off plus or minus 0.098 from each of those sample proportions, we have these so-called confidence intervals. Now, 19 out of every 20 of these intervals will capture that true proportion. One on average will not. That's the risk you're taking. And so that if we find a sample proportion to be 24.7%, we can use that estimate to compute the confidence interval. And that's like this red dot down here. And there's 95% chance that this interval will capture the true population proportion. And now we're going to look at another example. And this is a clinical trials involving flu patients treated with imbecile. And we're looking at a sample of 524 flu patients, of which 84 experienced nausea. And this gives rise to a percentage or point estimate of 16%. Standard error is given by this interval, this formula. Now, in this case, we're going to use our sample estimate, our point estimate, to compute this standard error, because we have no alternative. So putting 16% in there, we come up with this standard error of 0.016. And this represents the region about the population proportion, which 68% of the sample proportion should fall. Now we're going to look at a margin of error, which is your z-score corresponding to 95%, plus or minus 1.96 times your standard error. And this gives rise to 0.031. So this 0.031 represents the 95% margin of error, or basically a symmetric region about the population proportion, within which 95% of the proportion should fall. Now we're coming on the screen here, we're saying if we have one proportion, such as 0.16, we can use that as an estimate to compute our the confidence interval for the true population proportion. And that comes up on the screen here, 12.9 to 19.1%. 95% of all such intervals will capture the true proportion. And if the rate of nausea amongst patients given a placebo of 6%, we can see that this interval above is significantly above the 6%, and we're suggesting this constitutes sufficient evidence to suggest that the rate of nausea from use of imbecile is significantly above normal. And that's the end of presentation 7.6. We ask you to take notes as required and proceed to section 7.7.